Okay. Thank you so much for joining today. This is our interview session with Dr. Urmila Diwekar from Vishwamitra Research Institute. I would like to introduce myself and Shweta. I'd like to go first. I'm Debalina Sengupta. I'm the Associate Director of the Teas, Gas and Fuels Research Center at Texas A&M University. And I'm also the past chair for the environmental division, for which I'm conducting these interviews, especially because it's the 50th year celebration of the division, as well as 50 years for the Environmental Protection Agency, the NEPA Act, as well as Earth Day. So I think we have a lot to celebrate over the past 50 years, and we are talking with some of the stalwarts in engineering, especially in chemical engineering research, who have contributed towards this field. With that, I would like to turn it over to you, Shweta, and then we'll get started with Dr. Diwekar.
Yeah, really a great pleasure to join this conversation. I look forward to hear. And I'm Shweta Singh. I'm an assistant professor in Ag and Bioengineering and Environmental and Ecological Engineering. And I am joining this conversation to listen and also help Dr. Sen Gupta for editing and writing up the newsletter. So, yeah, thank you for inviting me.
With that, we would like to go to you, Dr. Diwekar. If you start with a brief, I know you don't have a brief background, you have a long background, but if you can tell us your current and past appointments, and then we'll take it from there.
Thank you, Debalina. Thank you, Shweta. I think it's a pleasure to meet you on Zoom now because of the COVID. At least we are meeting. And I to tell you my background, I think I have a PhD in chemical engineering. I was a professor in Carnegie Mellon University in their engineering and public policy and Department of Environmental Engineering for 13 years. Then I moved to University of Illinois at Chicago in their chemical engineering as well as Institute for Environmental Science and Policy. I was there for 2 years, and then I started a non-profit research organization called Vishwamitra Research Institute. I also have a special arrangement with the university where I am the main advisor for the PhD student I'm guiding, and I continue to do that. My focus of my research has been all the time related to environmental and sustainability, whatever required to solve the complex problems. So I also do some mathematical and computational research, algorithms needed to solve the large scale problems that we face in that area. Energy, environment, and sustainability is the main focus of my research.
Yes, thank you, Dr. Diwekar. What we know you as the main contributions are exactly what you said, solving large and complex problems in environmental research. And your contributions in that area has been very large and huge. So if you were to give us an overview of what you think has been the most important contributions in that field, and briefly if you can describe some of those. I'm sure we do not have the expertise to understand all of that, but if in clear terms, if you can explain some of your major contributions in the field.
Thank you. I hope, Miss, one of the things is that it's not that what contributions I have made, it's what problems I saw and then tried to solve the problem is the main thing. And I'll start with some of the problems my first PhD student where in Carnegie Mellon, we encountered the problem of nuclear waste. Okay, and the nuclear waste problem at Hanford, it still is a problem, and how to actually solve this problem. Many scientists have worked on it for over the years, and it hasn't been solved yet. There are 177 or more big, a million or more gallons of tanks of nuclear waste sitting underground in parts of United States. And the thing is that they don't know what to do with it. And one of the solutions was that we will form glass out of this nuclear waste. Okay. And the thing was, they were looking at what tanks to excavate, because they couldn't do half a tank processing. They had to do the whole tank. So it became a combinatorial problem, and they couldn't solve it because it became a combinatorially complex problem. So we had to invent new combinatorial optimization algorithms for that. Not only that, there were a lot of uncertainties. They don't know what material was there in the tank. In one of the tanks, they have disposed of a truck which got contaminated. They just dumped the truck in the tank. So how do you deal with uncertainty? And that's where I started my Center for Uncertain Systems, Tools for Optimization and Management, to gather multidisciplinary expertise on the, like, so we had something like 26 industrial and national lab advisors who were helping us, and the areas came out of it were algorithms, methods, and tools to solve these problems. Then materials modeling, computer-aided molecular design, so that we can design environmentally uh, benign products right from the start, which is a part of synthesis, part of process design, and then processes as well as going into manufacturing some of the things, as well as operations. So we were trying to do all these things. Energy and environment became the main field. So from nuclear waste to fossil fuel to fossil energy and to renewable energy, I have worked on all kinds of energy systems, chemical systems. Then as far as optimization is concerned, going from just single objective to multi-objective, to problems with uncertainty, whether decisions are discrete, continuous, or time dependent kind of thing. So the area of global sustainability, which involves large time span, okay, and you have to forecast the decision in the future. How do you do that, and how do you solve those problems? And that involved developing new methods, new approaches as far as algorithms are concerned, but also the solution to the problem were concerned. One of the areas which came out of that is the food, energy, water nexus, because the global models for that, and what policy decisions can we decide. We are engineers in a sense. We cannot live at the stage where we are saying, okay, this is the problem, that's it. And I can explain the problem, I can find, but we have to find solutions. And to find solutions means in some ways finding all these methods to solve the problem. Okay, and so that was the thing. So in some ways I have continued to work in green process product processes, as well as going from there to industrial ecology at the uh, to sustainable global sustainability level problems. There were a lot of things briefly in the manufacturing section. I had worked with some of the things in Ford for Ford Motors and other areas. We also work with small scale industries like NOx control, SOx control processes, environmental control processes, kind of thing. So it has been really rewarding. Some of the solutions are implemented in practice, some are still there, and there are a lot of problems to solve. So I think, and I know both of you have contributed a lot in this area of environmental research also. So I know uh, there are more individuals should come in the area and solve the problems that are there.
Shweta, over to you if you have a few questions before we go to the next sections.
I know that was a great introduction, and specifically this nuclear waste, and there is still a lot of mining going on for radioactive materials, and so I mean, I don't have any particular question. Just I'm curious that in your so many years of experience on environmental research and doing all these complex problems, what do you think is the industry's take? Like, how does your research impact industry, or have they taken some of these complex methods already?
The thing is, I think they may not have taken complex methods, but they have taken the solutions from the complex
Okay.
method. Okay.
Right.
So, for example, the NOx control technology, we worked with a small company in Pennsylvania, and it was a small grant from Ben Franklin grant from Pennsylvania. It was a Pennsylvania state grant. Okay. And this company was developing NOx control technology called low tox process. This process actually was using the same mechanism as that occurs in the atmosphere with ozone and NOx, to remove NOx. And they didn't have any uh, background in modeling and optimization of this process, so they couldn't optimize the performance. And what happened is that they came to us, and then we actually built things for them, and then they were acquired by BOC, and now the process has been a standard for NOx control in the United States and abroad. So that is one of the examples I can say. So many of the things which we have developed is much more algorithms and methods have been used, but the solutions are the main thing. That is. So recently, I was working with Dr. Rajiv Mukherjee on sensor placement problems. Okay, and we started actually sensor placement problem, which is again becomes a mitigation problem. It can be related to water, drinking water, to air, to to nutrients and things like that. So what we have proposed now is that in the cities, like many times there was a news actually 3-4 years back that in China the pollution has become so bad that citizens are buying cheap sensors and putting it on kites. Okay, and kites and generating data whether the pollution is bad enough to go out or not, that kind of thing. So that gave an idea about dynamic sensing. So now we just did a case study of Atlanta, saying that instead of doing steady state sensing, that you have sensing stations, if you can have drone based or a sensing which is changing with time, you can actually make impact on where actually the pollution is much more effectively, kind of thing. And that was actually funded by APRI. APRI thought that was great air pollution mitigation option. I don't know whether they're going to use it, but at least we have the methodology now to solve that kind of problem.
Yeah, those are very inspiring examples, Dr.
Yes,
Yeah.
and Dr. Devekar, one thing that I have observed regarding your work is that your work is bringing optimization and the optimization tools and models and uncertainty. You are one of the pioneers in uncertainty optimization. And how do you see that being utilized in some of the, of course, you have given some of the examples, but how do you think we can still continue to use it for some of the problems that we face today in terms of both environmental pollution control as well as the food, energy, water nexus issues that you have talked about?
Yeah, that's a great question. One of the problem why I got into uncertainties as a chemical engineer, I never learned it. We assume that okay, design is single value design. You cannot change it. And slowly you realize that if you look at environmental problems, especially risk, factors, they tend to be probabilistic, not a single value. And that's where the optimization under uncertainty makes a difference. For example, mechanical engineers deal with this problem in the reliability kind of area quite a lot. But for us, all this risk and so brings the uncertainty and things like variability has to be taken care of, because environmental problems they don't tend to be single valued solutions or single value, not solutions, single valued problems, So in the food, energy, water nexus, because the other thing happens there is that you are not just looking at something which is happening in just plant level, I can design, I work in distillation area, I can design a distillation column, say this is the reflux ratio, and people will use that reflux ratio in the plant. But when you try to, because we have good models for that, we have good thermodynamics for that. Not necessary every time, but good knowledge of a system because it has been studied for a long time. While when you think about food, energy, water problems, they are not at that level. They have level at the sector level, then at the global level, at the city level, where you tend to not have accurate physics-based models,
Mm-hmm.
and that's where the uncertainty can play, uncertainty analysis and optimization and uncertainty is needed, because you cannot say for sure this is what happens. So even take air pollution in the city, I cannot say that, okay, this is going to be the weather today and this is going to be the pollution today, because the weather affects the pollution, you know. So those kinds of uncertainties, even climate models or the weather models, they don't give you exact data. They are saying, I worked with Argonne National Lab, their climate scientist. This was related to water management in the power system, again, the water related problems. And the water consumption depends on the humidity and temperature at that point. So we were doing a case study for a day, just 12 hours. And I asked them, can you give me temperature and humidity for a day? And they gave me distribution all over the place, for whole day. They are not single value, because there are different kinds of models and they don't necessarily converge to one single temperature and humidity at one time, So even for one day in advance predictions, there is uncertainty. If I'm going to plan it for a month, that's going to be a problem, more problem. And if I am thinking about global or at the city or the country level, okay, at that level, you have to think about 10 years, 20 years plan or 100 years plan. We talk about sustainability, we don't know what will happen 50 years from now. So we have to at least plan for things, okay? So in that case, this kind of things are really useful.
So you touched upon a very interesting point about data and the availability of data. And in today's day and age, whenever we open any journal, any article, we are always coming across data analysis, machine learning, and these like advanced data analytics, if you will. So how do you think your previous work has influenced the way we analyze data, and how do you connect those to be kind of like in terms of the problems that you have worked on in the past and how we can work on in the future?
Okay, I think that's a very good question. As far as, yeah, right now, I think there is a lot of buzz about machine learning and data sciences. And a lot of statistical techniques have been used in that area. Some of the statistical techniques which are used in that machine learning and other things, we do use in what we say forecasting decisions in case of sustainability, global sustainability, So one of the aspects we have as engineer is that we have to do both statistical as well as physics-based models, because there is statistically I can get 100 solutions. Which solution is physically possible? So we have to combine both the things. So we had in the area of stochastic optimal control, we came up with ideas of how that can be used with physics-based model to forecast and the decisions and things like that. That can be useful.
Okay.
I hope I haven't worked much in the machine learning area, a little bit in the reinforced learning, but not much. But this is what I think from a top view, not the
No, no.
details I don't know.
Yeah, that's very good to know. So I think one aspect that I mean, this is again my observation, but you are one of the very few women engineers in the area of computing and systems technology and environmental engineering fields, whom we look up to as a role model to follow, because first of all, like the tremendous amount of computational contributions that you've made to the field, and of course, as a woman, that is something that we want to talk about. So, what are your thoughts on diversity in computing and systems technology type of work for the chemical engineering field?
Yeah, I think women, one of the things I'm very passionate about inclusion of women, because I myself had faced some discrimination in my life. And one of the fortunate thing is that I have a lot of supportive people in my life, which help me. But not necessarily everybody has that. And as a what I have noticed in my years is that these problems are not isolated. You know, my feeling is that every woman who goes through engineering, sometime in her life, she faces this problem. Maybe in a smaller scale or maybe in a larger scale. I don't know, but that is what my thinking, what my observation is, because I have talked to a lot of women students, even their parents sometimes. So I think that's where I really feel one of the this field, they there are not that many women, as you said. It's an unfortunate thing because we can contribute a lot, you know. And the other thing is, it's just that one of the things I noticed is it becomes a cultural thing also. It's not just this thing that makes it harder for women to get into things like this. But I think we are making progress, which is very good. And in fact, I think the Cecil Award, I was the first woman in 39 years of environmental division's history, you know. So 39 years, they didn't give it to any woman. That doesn't mean women were not qualified. It just didn't happen. So that tells you about. So I am really nice. It's really nice to see both of you contributing a lot and also surviving with flair in this
No,
area.
no. As you said, I think we do also have our own shares of uh, issues, but that has not been. But the people who are supportive are much greater,
Yeah.
and that I think has helped a lot. And I think the screen that we are looking at right now, three women, that's a great example of how we can bring this field together.
No, I also want to add that I think it is also because of role models like Dr. Diwekar, because I think having a role model makes so much of a difference because it gives you an inspiration and also kind of makes it seems like it's not impossible, because otherwise it becomes very challenging. So all the women who went before us, we have a great gratitude for them, and especially Dr.
The
Diwekar.
same way of applies to me also, you know.
Yeah, thank you. Thank you so much for that. Um, so you work with, I've seen you work with undergraduate students, graduate students, but also high school students.
Yes.
And you have published profusely with high school students even. So how do you think you are able to influence the next generation of students in coming into this sort of high fidelity work?
Yeah,
If you
I
have some
was
comments.
myself surprised because a lot of these high school students actually they contacted me, you know, and they showed interest in working. And I have not given them simple problems. I gave them hard problems. I had some of my researchers working with them, but what I have found is that they were themselves very motivated, you know, and because being an idealist in at that age helps, because then they believe that okay, if they can do something about environment, they can do something, and they really work hard and learn new things. And I never had any problems with those high school students. They did a really good work, you know, kind of thing. So I myself was pleasantly surprised. And many of them actually, sometimes their parents contact, sometimes they themselves contact, you know. So the current student who is working with me, she is joining Yale now. He was high school student, and he just looked at, he said, oh, you have developed that bonus algorithm. Can I work with you on things, you know? And then he's working on a completely different thing, biodiesel, okay? But he was happy, and he was just, I said, okay, read all these things, tell me which one you are interested in. And then they always, I have seen that they get more excited about environmental problems, you know, and
Okay.
then they choose that and then they work on it, you know.
Yeah, and bonus algorithm is hard. I have read that paper too.
Yeah, yeah, yeah.
So it's really
Yes,
good to
yeah.
hear that high school students are picking it up
And they
too.
themselves, as I said, he just came and he said, okay, I said, okay, read, you know, and this is and this is a long distance this thing, because these high school students are not, some of them are in Chicago, but they're not necessarily in Chicago, you know. But they read the books, they do assignments, and then they come back and solve the problem. So
So you
that
do,
was a pleasant surprise all along.
see, you have a structure to mentor these under high school students by giving them assignments as well.
Yeah, yeah, they need us, and they have done well, because after getting a publication or a presentation in AIChE meeting, they get admissions to really good schools, Princeton, Yale, and those things. So they also feel that there is something they can do, you know. So, so I think, in fact, one of my students who is a faculty in Rowan University, I told her, I said, Rowan has very good undergraduate students and this thing. I said, work with them, because what you need is a person dedicated to the to work. You know, they can gain knowledge by doing and reading and things like that. Not necessary that they have to have a degree, kind of thing.
Um, so if we go back to your career and your work and your contributions, so you have worked with industries, and I think Shweta touched upon this a bit. How have you seen the industry change its outlook towards environmental research and environmental applications in the number of years that you have?
Yeah, I think initially they were, in a sense, main thing for industry is profitability, but at the same time, initially they were very much interested in energy efficiency. If they can make the process more efficient, they make more profit, and the side effect is that environmental impacts are lower. Okay, first that drove him, but I think now they are realizing that all these problems are not necessarily going to go away, and they themselves are trying to get into environmental area. And I think Shweta can talk about it, like life cycle and other things. They are doing it diligently, at least because if you look at United States, uh, over the last, suppose, uh, few years period, many times the regulations are not they are loosening the regulations, but industries themselves are taking it onto themselves that saying, okay, even if regulations are not there, we will do our part a little bit. So I think there is a change. Previously, it was not, unless we had to convince them where that this is actually makes difference in your profitability, then they were doing it. Now I think they also realize that in the long term it's good for them, because the image matters, whether they are doing good for environment or not. So they are changing.
So the next question that I have for you is, you have been involved with the environmental division, and you said you were the first Cecil Award winner. What has been your association, and how have you seen the environmental division help in formulating the future of chemical engineering research in environment?
Yeah, I think I have been involved with environmental division. I was a programming chair as well as director for some time. So I have this. So I think environmental division also evolved over time. When I joined environmental division, there were not many young people joining that time. Okay, so what was happening was most of the even the office bearers were older people, not younger people. So what happens is that if younger people are not interested, then the area doesn't go further, because you need next generation there. And I think over the years it has changed, and I think all you people are involved and things like that. So younger generation started getting interested, and that is really good for environmental division. Uh, Obviously, they do programming in various areas that has changed over the time also. So for example, sustainability got added as a new area, process development and things like that. So they changed their scope as the time goes by. There was a time I remember in the discussion that this was maybe in early or late 90s. Okay, late 90s, that they were thinking that environmental division will be obsolete because our people are solving environmental problems. And this was a discussion there, and that hasn't happened, because as human beings, entropy is always increasing, right? So it's not going to be solved in all generations. But that was the thinking at that time, that we have solved all the major problems. Now what will happen, kind of thing. So that hasn't been the case, and it is a very what I would say important part of AIChE, you know, and it has even if Sustainable Engineering Forum came, that time also there was a fear that environmental division may not be relevant, kind of thing. But the thing is, they survived and grown quite a lot. And I am happy to see a lot of young people involved. That is important.
I think what the difference between Sustainable Engineering Forum and Environmental Division is, the Environmental Division deals with a lot of the fundamentals of air, water, hazardous waste, and the theoretical approaches associated with that, whereas Sustainable Engineering Forum is kind of complementary and puts everything together. So I think both of the divisions, or the forum and the division, they have their own niche areas and how we can make things work. Again, sustainability is, as I kind of mentioned, there are two ways of looking at sustainability. One is the hipster sustainability kind, where you are doing all the fun stuff of using a reusable water bottle or some things that are easier to do. But again, to go to the fundamentals and the core, you need to have your roots in the environmental engineering
Sure, yes,
domain.
definitely. And I think as a chemical engineer, because one of the things I have noticed, because since I was a part of environmental engineering departments, that most of the departments are in civil, you know, but what chemical engineers bring in there, because we have a knowledge of reactions, which
Yes.
all these people lack, and that is a main part of environmental plus and minus, you know. So understanding that brings in a lot of things to the environmental area. So as a chemical engineer, we can contribute a lot, you know, because we have that understanding. That makes it a difference.
I think that is a very important point that you touch upon, is that the environmental engineering has kind of shifted to the civil engineering department. But whenever we talk about controls and all these
Yes,
theoretical models and instrumentation,
yeah,
it it is
chemical
modeling
engineering.
the reactions, and that is chemical engineering. And do you see a disconnect that has happened over the years with chemical engineering departments in general, that we have moved or shifted the environmental focus? Or how do you think that has affected in the chemical engineering departments as such?
Yeah, I think what happens is that there is always this hype of one of the areas. So, for example, now a few years back, there is hype about bio. Okay, so the chemical engineering was thinking that bio is going to be a big thing, and they actually the departments are filled with bio faculty. And what I since I work in separations also, a lot of industries were complaining that the students which are coming out of department, they don't know basic fundamentals of separation, because bio uh, faculty they don't want to teach thermodynamics or separations and things like that. So I'm just saying, many times departments are short sighted. They go by the funding cycles, and funding cycles are, this is like one of the things, it is, there has to be a newsworthy thing. Okay, then the funding cycle goes, okay, so currently what is the keyword which is generating hype, will fund those things, kind of thing. And that makes it a problem, because some of the areas are fundamental to the department. Okay, and you should have that. But as I said, that this is something, especially in United States, other countries are less likely. They keep their basic fundamentals education, because US allows a lot of flexibility. The department change their uh, their focus quite often, and that can be detrimental. It means that's what I have seen in many things, so many departments over the period. And as I said, industries and people who are hiring, they complain about it.
Mm.
Even PhDs, they say, if you are not academics in the bio area, you get technician's job, not engineer's job, you know. So
Mm.
that does happen. So I'm not saying bio area is bad. I'm just saying everything has its place. You cannot remove fundamentals and have something new replace it. You have to have both. You can have the bio, but you also have environmental. You also should have design. You should have thermodynamics. You should have separations, you know, to reaching that.
I think that is very important for the design problems, the senior capstone design
Yeah,
problems that we have to solve.
yeah,
And I am at the heart of like oil and gas business in
yes,
Texas. And if we do not teach our students about how to design a column or a separation unit, they are not going to survive in this market.
yeah,
So that's something that
exactly.
we have to hold on to, like some things. And then adding the environmental parts. There comes a question of if you can give your thoughts on how we can integrate more of these environmental concepts into design for
Yeah,
engineers.
yeah. No, it is very important, and I think here I will quote Bhavik. Bhavik does Bhavik Bakshi, Shodhvita's advisor at Ohio State University. He does a course on sustainability and environment, especially life cycle and other things, and for all engineers, so the environmental should be part of everything, because if you start becoming aware of things right from the beginning, then I won't think about designs which can cause environmental problem. I will always be this thing. And what we have seen in the environmental area is that if the thinking starts at the level where even the products are not yet produced, you can make a big impact as far as environmentally benignness is concerned. So you have to think much proper. So in the design courses, if you think people can think about life cycle analysis or impacts much earlier, then they will, because there are ways to make sure that happens, that you get environmentally benign design or environmentally less pollution if you can design it properly. And if that idea is stuck in your mind, when you go in real practice, you will always do that. So there are two things people think about: either a dedicated courses or have each course an environmental component. So for example, if I am teaching distillation, I have to talk about energy efficiency and other things. I can talk about some of the ways I can reduce those kinds of things. But so separations processes, or if I am talking about thermodynamics, then I can talk about some of the entropies and things much more, uh, uh, much more as far as the environmental problems are concerned. So each course could have environmental component and a dedicated course. So that would be good for students. But I think, yeah,
Go ahead.
but that will need dedicated faculty also.
Mm-hmm.
That is all right.
So I have a follow-up question on the issue of like these new emerging areas and then the department shifting their focus. But
Yes.
so my question is on how do we integrate the emerging areas with environmental education and chemical engineering? Because like you work in complex systems and nothing is isolated, so
Yes.
eventually the industries, even the chemical industries, are moving towards bioprocessing or genetics based
Mm-hmm.
designs, and those will come in the process design eventually, right?
Yes.
So what are your thoughts on like if younger faculty or researchers are thinking about integration, that what is the
Yeah.
key low hanging
Mm-hmm. Mm-hmm.
topic?
I think I don't know much in the bio environmental area, but what I am seeing is that even any process, if you think about fundamentally, whether it's a biological process which we are implementing in industry or a distillation, uh, entropy is increasing. Okay, so thermodynamically, if you can think about it, you are essentially saying that yes, it has impact and it needs to be considered. So you have to. Right now, there may not be approaches to solve this problem, but I think that's where you have to think about it, how to do life cycle, suppose, about the biological process. You may not have data and all, but somewhere somebody has to start. you know so if you put that in minds of student, at least that they have to look at it, whether it's there or not, it will start. you know People haven't thought about it. Many of them are at the cell level and things, they think it doesn't matter, but it matters. It matters a lot, whether it's at that level or not. And my feeling is that what we have learned as a chemical engineer in thermodynamics, kinetics, and other things, this will be applicable to biological processes also. So for example, the research I did in vitro fertilization, actually that was a completely biological process. But in my mind, when I looked at it, it looked like chemical engineering particulate process, you know. And I applied those principles and it worked. So I'm just saying we can extend the principles which we think. Uh, so at least we have learned the things which will be making a lot of difference in this area. It hasn't been applied, but I think there is a promise there.
I think you touch upon one of my favorite areas of your work that I really respect, and that is the in vitro fertilization. So, if you can expand a little bit more on that work and how it was
Yeah.
impacted, the impact that it has had.
Yeah, this is in vitro fertilization is a treatment women take if there are fertility issues, maybe because of age or any other factor. I myself went through a lot of in vitro fertilization cycle. And what they involve is the hormonal injections, daily ultrasound, and daily blood work. Okay, for the woman, for something like the cycle is maybe a 15-20 days cycle. Okay, and that means a lot of emotional problems. Lot can be if you get more hormones than necessary, it can be fatal also. Okay, so when I was going through that cycle, what I noticed, because I did cycles in United States and then in India. In India, the doctors were giving half the dosage than in America. And I was just, and results were not much different. And I was just wondering why that is the case. The case was not that necessary Indian doctors were more intelligent. The cost is a factor. They tried reduced dosage and it worked, and they didn't bother about it. In fact, I had asked my doctors, because I was giving thumping dosage, the same dosage like a big, tall American woman will get. And I actually had a overstimulation problem and was admitted to emergency because of that. And that's where I realized that something can be done here. It's a chemical reaction after all in the body. And what happens in vitro fertilization is they actually develop more follicles, eggs in women's body than normal. Normally there is one egg per cycle, per menstrual cycle, and that egg get fertilized and then maybe implant. But in vitro fertilization, they need multiple follicles. So what they do is they give hormone dosage, do ultrasound, find out what the follicle, and the follicles have to be of a particular size. Once they reach that size, they break on their own. So you only can grow follicles up to that size. The first particle which becomes that size, cancel, the cycle is complete. Okay. So at the end of the cycle, when first follicle becomes 22 mm diameter, you want to have as many follicles close to that diameter as possible. Okay. And so essentially every day you look at that. It's an emotionally taxing process also. It's really, you worry, it is developing properly, not developing properly. So what I was thinking is that this is like a crystallization, because in crystals grow. Okay, it's like a particulate process. You reduce temperature. If it is temperature crystallization, you actually make sure that the crystals, and then we have in crystallization also that quality control, saying the crystals of same size have to grow. So they have developed nice optimal control methods to make sure that crystals are of same size. So at the end of the time, it's a batch crystallization. So I said, can I use similar thing? Crystallization, especially with the chemicals, is a reaction again. Mm-hmm. So the equations, which is particulate process equations, dynamic equations with how the distribution of each crystal is, the size distribution. So I said, this is also size distribution. So we actually use an analogy between crystallization and in vitro fertilization to derive models. And what we found is that we could actually reduce the dosage by 40 to 60%. Mm-hmm. Okay. That means no overstimulation, because that means the side effects cannot be there because you are reduced dosage. And testing is reduced because you are not monitoring the every day the size of the particle, because the model can predict what happens. And you can actually control it. So we use some of the optimal control theory. And we did clinical trials also. And what we found is we could give more follicles of same size than the doctors could do with less dosage. So right now, I think I am starting 3 clinical trials, big hospitals in India, in Bombay. And there is a software and maybe an app for doctors, because they need, and this is customized for each patient, because what we do is we are using first 2-day data for each patient. And then say after 2 days, you don't need to come and test. First 2 days testing is necessary. So out of this 11 day when they do testing, only 2 days testing is necessary. And we are predicting whether the cycle will be failed so that you don't have to go through the complete cycle. So I think it has a great promise, and it's for just my chemical engineering knowledge, which has helped me to actually model a biological process. And that's why I think it's possible, because
I really wanted, even though this is not as much environmental, but this shows what potential chemical engineers have in impacting any problem in the world.
Definitely. It's a public health issue also.
It is a public health issue, and whenever we look at physical systems and more of human physical systems, we are a chemical compound.
Yes.
A very complex chemical compound, and some of the issues we have separation processes every day. We have absorption going on in our body every minute.
Yes.
So I think that way we have a lot to contribute if we were, and I really wanted to the chemical engineers to know about this very innovative and very practical research that you are conducting both in US and India as well. So thank you for giving that.
It is personal for me, actually. It's a women's issue. It's a thing.
Now, this is very impressive, but I would like to add that this reduction in testing and reduction in emotional, we cannot quantify that, but with reduction in testing, there is an indirect positive environmental impact, because you're not using more machines, less energy. So the life cycle thinking brings in that this is definitely has a positive environmental impact as well.
Thanks.
No, and especially the cost as well. In sustainability, we often overlook the cost, but the cost is one of the major concerns for a lot of women to go into such in vitro fertilization issues, especially in countries like India, and where women want to become mothers, but they do not have the necessary means in terms of money.
This will reduce the cost quite a lot. In fact, even here, the insurance don't cover more than 3 cycles. Because good insurance, I'm saying others, I don't know. Good insurance don't cover more than 3 cycles. And the thing is that it is a trial and error process. So people want to have, it went up to this point, maybe next time, kind of thing. And that's why I went to India, because after 3 cycles, I said, okay, I'll try in India. And I found that they are just doing half the dosage, and the results are not different. Why is that?
So, Dr. Diwekar, this has been a very interesting conversation as well. But what message do you have for the younger generation in the future? I know we are going through COVID-19 times, so there will be pre-COVID-19 and post-COVID-19 situations. But what do you think that we, and as well as younger than us, like maybe my 5-year-old, what message do you have for us going forward, both in terms of how we look at the future in any direction, not only environmental engineering, but also chemical engineering in general, and how do we look forward to life?
One of the things I think that as I said earlier, the problems are not going to go away, but there is a way to find solutions. So at some level, we have to prepare the young generation for getting to the solution. Things are going to change for them all the time. So pandemic is right now a problem, but it's not necessary this is the only pandemic we are going to face, because there will be more things. And at some level, even climate change is a big problem right now. We don't know how to address those things. So how did we get here? The history we have to look at, and how do you get out of it is, and that's where the thinking is that even if you do one step at a time towards the solution, is better than thinking that I cannot do anything. So here I can maybe say a joke about engineer, you know. So this is my favorite joke. There was a mathematician and engineer, graduate student, and they went for a party and they saw a girl and they liked it. And they said, okay, this person said, I will ask her out. Mathematician said. Engineer said, I also want to ask her out. And her father comes from behind and he says, well, if you want to ask my girl out, you have to solve this problem. You take one step towards her, next time you take half of that, okay? And then reach her and then ask her. So mathematicians goes, first step is x, next is half x, third is 1/4 x. This is a series, this is an infinite series, I'll never reach her, you know. The engineer, he didn't care, he just goes and he says, okay, I'm just walking towards her. So the mathematician asked him, don't you know there are infinite steps, you cannot reach her. He said, I'm an engineer. If I reach her within tolerance, that is sufficient for me. So we have to find solution. That is very important, you know. So and that's where in some ways engineering mind is useful, because we say, okay, even if it is approximate, it's possible, but I can take first step. That is important.
I think that is a very nice note. If Shweta, do you have any other questions?
No, not anymore. But yeah, this was very, very. It was a pleasure to hear and inspiring. And I like the joke of reaching the sustainability challenges with intolerance. So I will keep that in mind for my future research.
I think so too. Like, as long as we keep within the tolerance limits and not do too much overboard. Thank you so much. This
Thank
has
you.
been a pleasure talking to you and learning from you, most importantly, being the inspiration for a lot of women engineers in the field. Thank you so much for your time and your contributions towards chemical engineering.
Thank you. Thank you very
Yeah,
much.
thank you.